Okay. Hello everyone. Good afternoon. I hope that you had a great lunch. Feel free to sleep if you want. I understand. I would be asleep if I were you. First of all, I present myself. I'm Felipe. My last name is Garrido, but I'm using for academic purposes my second last name, which is Goicovic.
It's an artistic name.
My artistic name is Felipe Goicovic. So if you see a paper Goicovic, that's it. And today I'm going to present part of my PhD thesis. I'm a PhD student at Universidad Católica de Chile. And this topic is going to be much more specific than the previous two speakers. So if something is not clear, if I'm skipping something or you need more clarification, you can ask me. Please feel free to interrupt me. So let's start. The topic of my thesis is Infalling clouds. Infalling clouds onto massive black hole binaries. Okay? So now we are changing topic from these stellar mass black holes to massive black hole and binaries. My thesis is modeling the interaction of a cloud with a binary of supermassive black holes. So of course a little bit of introduction first. You all know that we have supermassive black holes in the centers of most galaxies, and galaxy mergers will lead eventually to the formation of binaries of these objects. The observational evidence for these binaries is scarce. We have a few candidates, and most of them can be explained with alternative scenarios that don't involve the presence of a binary. So that's something that is in progress, looking for these binaries. We know that they should be there, and it's probably an important phase of galaxy evolution, especially considering that they had a key role in the evolution of galaxies through AGN filter, for example. So, why we are interested in these binaries, of course, during the merger of these two binaries, this will be the source of gravitational waves by excellence, because this very extreme system is going to be very luminous, in quotations, in gravitational wave emission. That will be detectable in the future, let's hope, with ELISA or PTAs. So, but by now, we need to, because we don't have at least the sensitivity with PTAs, and ELISA is not in space right now, we need to have other tools for studying these things. So now I'm going to talk about something very important, which is called the final parsec problem. Yes, we have what I call the binary path to coalescence. This plot is a ripoff of Begelman's in the 80s, where this is timescale of the evolution of the semi-major axis of the binary, and this is separation. Yes, we have three distinct processes acting in the evolution of the binary depending on the separation. We have first, after the merger, that the two black holes will sink due to dynamical friction with the dark matter and stars. This is called the pairing phase. Yes, and then when the separation of the binary is of the order of this value, which means that more or less when the mass in stars inside the binary orbit is of the order of the binary mass. The process is inefficient, the dynamical friction is inefficient, So we will start hardening the binary. At this moment, we call it a bound binary. But now, we need to harden the binary with other processes, and we will have, for example, a scattering of single stars, and with that we will be hardening the binary. So this is the hardening phase. And when the separation is sufficiently small, we'll have the gravitational wave emission, which is extremely efficient, extracting angular momentum and energy of this binary, leading to coalescence. So gravitational wave emission. And for example, in a gas poor system, the amount of stars that you have in the lost cone, which is with orbits that can interact with the binary and extract energy and angular momentum, it's being depleted. So the process is evolving the separation is becoming more and more inefficient. So when this timescale is larger than the Hubble time, this is what we call the last parsec problem, or the final parsec problem.
The timescale is something like the separation divided by the rate of change?
Exactly.
Oh,
Yes.
cool.
This is a dot. No, it's
One
A
minute.
over A dot.
Right.
Yes. That's the time scale of evolution of the semi-major axis. Yes. The final parsec problem. Of course, there's been studies that claim that with changes in the distribution of stars, you can have more centrophilic orbits that can refill the lost cone more rapidly, making this not as inefficient as in this example. But of course, we don't know exactly what is happening because these scales are really small to be resolved in galaxies with the current capabilities. So now and then, being that probably stars are inefficient in extracting the angular momentum of the binary, I'm interested in the interaction with gas. Why? Gas is much more efficient extracting and transporting angular momentum of the binary than stars. This has been studied a lot using theoretical and numerical techniques, and it's probably very relevant through a circumbinary disk. The problem is that this, for having a circumbinary disk, you need to transport gas from kiloparsec scales down to parsec scale, which is the separation we are talking here. So we need a process that efficiently can fuel the galactic nucleus. So in my thesis, I'm using the hypothesis that if the interstellar medium is turbulent and or gravitationally unstable, you can have the formation of clumps or molecular clouds that can travel more easily through the interstellar medium because they are more dense than the average density, and the hydrodynamical drag doesn't affect this clump that much. So it can refill the galactic nuclei, it can fuel the galactic nuclei with gas, and of course interact with a putative binary. So this is the topic of my thesis, and also why gas is important, because it will produce an electromagnetic counterpart that is something that is very it's very relevant, even when we have when we will have this gravitational wave signal, because we need to point where the source of this gravitational wave is coming. So we need these electromagnetic counterparts, and of course gas can be very luminous, especially if it's close to the black holes. So I'm going to present now my numerical model. Yes, I'm modeling numerically the interaction of this of a binary with a molecular cloud using SPH simulation and SPH code, sorry, and smoothed particle hydrodynamics, which is very famous. You probably heard of it. It's Gadget. I'm using Gadget 3 to simulate the interaction. So how's my system? I put a binary. Yes, and this is very difficult to plot, and I'm just throwing a cloud into this binary. So I'm putting an initial velocity. Yes, the initial velocity field of the gas is turbulent, so we have a turbulent cloud. Yes, the binary is equally massive, so Q equals 1, and circular. And the mass of the binary, the total mass of the binary is 100 times the mass of the cloud. Yes, of course I'm modeling this using code units, but with a standard scaling. This binary is separated more or less 0.1 parsec, and the total mass of the binary is 1 million solar masses. That's the number that you should keep in mind. Okay, and of course, when you have a binary, you have a preferential direction, which is, of course, the rotation axis. So we want to study the implications of different orbits, initial orbits for the cloud. So we are modeling different impact parameters and also different orientations.
Do you have star formation, your molecular cloud? Okay.
No. I'm using an equation of state which is dependent with the density.
Mm-hmm.
After a threshold, I'm using, for low densities, I'm using isothermal, and above some threshold, adiabatic region. So it's a very simple recipe. Of course, during the...
Maybe, I guess, if I remember correctly, the orbit of the cloud is very eccentric, right?
Yeah,
So
I forgot to say that. Yes, I'm modeling orbits that are very eccentric in order to have a very strong interaction, a transient evolution which is very strong. So I'm choosing this initial velocity to have a bound and a very eccentric orbit. Thank you, Masi. I forgot to say that. So I'm modeling a total of 13 systems, changing the impact parameters and inclinations. The inclinations that you should keep in mind, I have to draw them because they are very difficult to explain, at least a line, which I call the A models. This is, of course, very simple. We have the binary rotated like this, and the cloud is in the same plane and co-rotating with the binary. This is the align models, counter align, which I call CA, is if I put the binary rotating like this, now the cloud is in the same plane but counter-rotating, and two perpendicular, which we thought are the two independent directions, perpendicular directions, perpendicular edge on, which I call the PE models. So now the binary, I'm not using the space very well, the binary is moving in this plane, so like this, do it like this, and now the cloud is coming like this. So that is why it's edge on. The binary and the cloud start in the same plane, but the tangential velocity of the cloud is perpendicular to the binary. And finally, the perpendicular face on, which I call the PF model, and now the binary is moving on this plane, and the cloud is coming like this. So the cloud starts in the perpendicular plane respect to the binary. So it's coming like this, hitting it face on. Of course, if you want to see some animations, you can go to my website. I'm going to put the link here. Usually I show my animations in a projection, but of course I don't have it here. So you can go right now and wake up.
But how does it allow?
Exactly.
You can draw, erase, draw, erase.
Ray tracing by hand.
Okay. www.astro.book.cl/this thing F Garrido. And animations. Yeah. So you can wake up now seeing these animations in order to understand this all these different orbits more clearly. Now, this is my model. This is what I'm doing. The first part of my investigation, actually this is already published, is the formation of disks around the binary depending on the different orbits, initial orbit of the cloud. So you can go check my paper. But right now, something that I think is more relevant for the topic of this workshop, I'm studying the binary evolution due to this, the orbital evolution of the binary due to the interaction with these clouds. I'm also modeling, I mentioned 13 systems in total. These are 3 systems for these last 3, and 4 systems, 4 impact parameters for this, for the first. So in total 13 systems. Okay, now the first thing that we needed to address after we had the simulations was if we had the sufficient resolution to see the changes in the binary orbit robustly. So we study the angular momentum conservation. We compare the evolution of the total angular momentum of the system, that is gas and black holes, and also the angular momentum of the binary itself. When the evolution of the angular momentum, the binary angular momentum was very high with respect to the fluctuations in the total angular momentum of the system, we could resolve this evolution. So we found that we could resolve only the transient evolution of the binary due to this interaction. So the first few orbits. After the first, let's say, 8 orbits of the binary, the angular momentum evolution was consistent with the numerical mass. So you should keep in mind that all the results I'm presenting here is just the transient evolution of the binary due to the interaction with this class. So of course something that is very important is this is the compilation of all the results of this simulation, and that is the evolution of the semi-major axis with respect to the initial value for the different orbits as a function of the pericenter distance for the different inclinations. So we have here, this is 0, and we had for the aligned models, we had something like that. We had that the evolution of the semi-major axis was positive, meaning that the interaction in these cases, this is the aligned case, was always expanding the binary, contrary to what we initially expected. And in the other three cases, we have a negative evolution. So we have here. This. Yes, that was the perpendicular. I'm going to put labels soon, so don't worry. It's difficult to draw your plots in a blackboard. So we have negative evolution for the other three systems, and of course, as we wanted to study a more continuum distribution, we extrapolated results. We put some lines here, just linear extrapolation of the data. So this is the aligned models.
Then you have other colors as well.
I think we can.
Oh, that's true. I should have started with different colors. This is my first time.
Carlos is colorblind, so it's not making a difference.
Okay. So we extrapolated our results, and
Actually, it's not very different.
come on,
Maybe I'm not a colorblind person.
I missed the point. It was this other point. But it doesn't matter very
You
much.
can do dash and dash dot and all that.
No, it's really
It's
more difficult. Okay, but it doesn't matter. So we have, this is the perpendicular face on, perpendicular edge on, and the counter line. So this is the transient evolution of the binary due to the interaction with this cloud, and a compilation. These different points are the measurements from the simulations, and of course we extrapolated those results. You're going to see in a moment why. So now we need to erase because I'm out of space.
Simulations.
The period.
Hmm?
The period doesn't make sense.
And the worst
Is
managing
it
the
the period?
space in the
No, it's the percent.
The percent
passage.
It's the pericenter passage.
Ah.
And this goes, I should have said that, this goes from 0.35, the initial separation. This is twice this value, and this is twice this other value. Okay. So the first one is less than the binary radius, and the other are larger than the other. But it's still having this very eccentric orbit. Okay. So now that we measured the evolution of the binary, we wanted to understand what was the process behind this evolution. So we made a simple analytical model. Considering the exchange of angular momentum between the binary and the accreted gas. Okay, I'm modeling these black holes using zinc particles, which means that this is a particle that only interacts with the other zinc particles and with the gas particle through gravity, and within certain radius, all bound particles are added to each black hole, to each zinc. So we are modeling now. We wanted to make a simple model of a change of angular momentum between the gas and each zinc particle through the accretion, which, of course, given the numerical barrier of not being able to resolve the event horizon or the ISCO, we are using a very large accretion radius compared to the Churchill radius. It's orders of magnitude larger than the Churchill radius. So when I'm talking of accretion, I'm really talking about capture of material. This is material that is captured by the black holes, and in that process, you are exchanging angular momentum. So, of course, when you have initially the aligned case, you will have that the binary angular momentum is pointing like that, so you will be adding some angular momentum of the gas which is in the same direction. Yes, this is the aligned case. And the counter line is the other way around. So this is the binary, and this is the gas. Counter line, put it like that. And in the perpendicular, it's just perpendicular. Okay, we're saying that, and the first hint was that in the case of a line, we are expanding the binary, so we are increasing the angular momentum. And that we can understand that through this. We are adding some gas with angular momentum that is in the same direction of the binary. And in the counterline case, you are subtracting a lot of angular momentum, and sorry, and for the perpendicular, sorry, I should. For the perpendicular cases, you are not changing much the I forgot the size model. It's okay. The magnitude of the vector, but we're changing the inclination. So the main effect of the perpendicular encounter will be to tilt the binary. And actually we confirmed that with the simulation. We saw that the binary is tend to tilt when it's interacting with a perpendicular cloud. So now we
Quick question then. Just so the fact that the semi-major axis is dropping for the perpendicular cases, is that simply because what you're adding mass to the system?
I'm getting to that.
Okay.
Yes.
So the angular momentum of the gas is pretty much negligible compared to the angular momentum of the binary, isn't it?
Not really. It's
The binary is much more massive.
what's negligible? It's at best a few percent. Yeah, maybe.
So you cannot use the binary too much.
No. It's actually the largest. I think is the perpendicular edge on is 1 degree. So it's not a very huge
Do
evolution.
you want to put some units in the tertiary array as well, so you have an idea?
You mean the values?
Yeah, like 0 and the other values are.
Should I put this is around 1%, and the more extreme case which is this is 7% of the order, more or less, a little bit less than 7%. Okay. Okay. So we want to model the evolution that we are measuring through this. So we want to estimate this. So we do that like we write the angular momentum of the gas as an alpha, the gas mass that is captured, that is considering this angular momentum that is captured, with this form. And this comes from the initial conditions, because of course I'm putting an initial velocity which is some fraction of the circular velocity of the binary, and also and that's it. And that fact is captured here in this alpha. This alpha is changing with the impact parameter. Okay. So we write the angular momentum of the gas like that, so we can say that the change in angular momentum of the binary initially will be the capture mass or the accreted mass as a function of the initial mass of the binary. So we are just using the fact that the angular momentum of the binary, you can write it like the reduced mass and this square root here, and the reduced mass for an equal mass binary is 4m, which is the total mass of the binary. Okay? So we have this model, and when we compute the angular momentum evolution using this expression, we reproduce the trends, but we couldn't reproduce the exact values. We were not close to the values, so we were missing something, and that's why we had to add a new term which we call L out, which is the because we were ignoring the gas that was not captured, and this gas was interacting with the binary, especially through slingshot. So in the perpendicular cases, even though you were just tilting the binary, you were slingshot some material in the same plane of the binary, so you will shrink a little bit the orbit. So that's why we had to add this last term here. So this alpha is a measurement of the average angular momentum of each gas particle. This is the total captured mass, and this is the slingshot material. And with this, we reproduce all the evolution within a few percent. So now we understand what was happening during the first few orbits of the interaction. Okay, so it was capture of material, and the material that was not captured, some of it was slingshot, and can further evolve the binary. So we understand the evolution. And furthermore, with this we can compute the angular momentum evolution, but we also can compute the semi-major axis evolution. And with that, we use that the angular momentum of the binary can be wrote as okay, and we can transform the reduced mass, which is not very useful for us, to mass ratio and mass, and we have something like this. Square. So we can differentiate this, and we can relate the all these components, the change on all of these components to the change of angular momentum, and we differentiate, and we have something like this. -1 Q and Q is M plus N or A minus delta E. Okay? I want to keep this, but I'm using this. And given that the binary is initially equal mass, and the accretion is not considerably large with respect to the mass of the binary, we have that this term is approximately 0, and also the binary is circular, and that doesn't change much, so we have only this term equals to 0, and now we can write this, the evolution of the angular momentum as a function of the evolution in mass and the semi-major axis, and computing the angular momentum with this expression, and this other one we can, of course we have here the change in mass and also here, so we can have the we can compute, we can estimate the evolution of the semi-major axis using this. And again, we had values that within a few percent of the actual measured values from the simulation. Okay, so we understand why the evolution happens like that. And now we can move on to the next step. I don't know what to do now, because I don't want to erase everything. I think that one is more important than this one. Can I erase this? So now that we have these, all these results, and we understand what is happening, we want to apply this, actually this, to a binary embedded in a medium where it's interacting with several clouds. So the application, we call it long-term evolution via accretion of incoherent gas pockets. So we are making a very simple model, drawing clouds from a Monte Carlo sampling with different orbits and different levels of anisotropy, meaning clouds coming from different places, and evolving the binary according to these values that we have here, in order to compute a timescale of evolution, driving this binary to the gravitational wave regime. So we are drawing clouds from using first we need the angular momentum direction of the cloud's orbit, and also the magnitude of this vector. So we want to draw different angles, and this is going to be very difficult, so be patient with me. I'm trying to draw a hammer projection of the angles that we are sampling. So this is a basketball. This is theta, and this is phi, so the inclination angle and the azimuthal angle. This is 45, this is 90, 135, 180, and this is 0, 90, 180, and minus 80. So we need to draw different angles, and I'm going to show that here, because we only have 4 directions, which are very, how to say, extreme. This is just, for example, the align, it's going to be here, and the perpendiculars are going to be here and here, for example, and the counterline here. So if we draw different angles, we need to relate these angles to that different inclinations. So we arbitrarily define that from 0 to 45 in theta, for every phi, we have align orbits. The same here, the same thing here. All these, the angles here are going to be counter-aligned, and the perpendicular, maybe I can use different colors here. For example, here is going to be perpendicular H1, for example, and here as well. This is very arbitrary because, of course, we are not, this is not very representative. All these angles are not all similar to this, but we need to start somewhere. So this is perpendicular H1 as well. And this is perpendicular face on. And this as well. Okay, and then we align and counter align. So we relate these angles to our different inclinations, and we draw different levels of anisotropy. These are called F distribution, which Massimo is probably very familiar with, because he introduced them in one of his papers. We modeled three different f equals 0, f equals 0.5, sorry, f equals 1, and f is the probability of having events in the southern hemisphere. So f equals 0 means 0 probability of having events below this 90 in theta. So this is mostly prograde. So we have only events in the northern hemisphere. With f equals 0.5 is equally likely to have events in the southern hemisphere than the northern hemisphere, so this is isotropic. And this is f equal 1, so every event is going to be in the southern hemisphere. So mostly retrograde. Okay, so mostly retrograde because, as you can see here, you can have still perpendicular encounters being in this edge here. And the same for the prograde. Mostly prograde, but some other perpendicular cases. Okay, so this is just for drawing the angular momentum directions. But we need the magnitude in order to have the full initial orbital description. So a measurement of the magnitude of the angular momentum is the impact parameter or the pericenter distance. So we are saying that the clouds will be having a uniform density distribution. That means that the probability of having an event with a certain impact parameter, this is not the pericenter distance, this is the impact parameter, goes with the impact parameter. And if we assume that the initial velocity of the cloud is small compared to the velocity of the binary, the encounter will be dominated by the gravitational focusing, and with that we can transform the probability distribution of having a certain pericenter distance, which is going to be a constant. Okay? Because the pericenter distance for a gravitational focusing dominated process goes to as b squared. So we sample the pericenter distance uniformly between 0 and some max value. Okay, and the maximum value is going to be given by the extrapolations in this of these measurements. So with that, we have all the orbits for our clouds, and we draw, we run very different Monte Carlo distribution using these three different levels of anisotropy.
Just a question. Is this a loss? So you're assuming that the distribution of the clouds, the density is homogeneous.
Yes.
And then the probability density goes as b.
Yes. It's homogeneous in space and velocities. This is isotropic, yes.
So it's it.
So the probability of having clouds with a certain
B
B goes with the area. So if you
with the area.
yes, because if you have your binary here, you have this B. The area of this ring, this cross section, is
Okay, so
increases with the B.
true. You're right. Yeah. Sorry.
Oops. Okay, so we draw these Monte Carlo runs with these different levels of anisotropy with uniform pericenter distances, and with that we can obtain. This is the main result of this paper. First, the evolution of the semi-major axis as a function, of course, of the initial value, and against the number of encounters. So we start in 1, so this logarithmic scale, 10 to the minus 1, 10 to the minus 2, and we will have 3 different lines for the 3 different levels of anisotropy, and this is linear. Okay, so this is f equal 0, f equal 0.5, f equal 1. So we have this the devolution in logarithmic scale with the as a function of the number of encounters goes linearly, and this is more or less 1,000 clouds. This is more or less 400 clouds, and this is 200, more or less. Of course, this is not very useful because it's in the number of clouds, and we want to change this axis for time. So in order to do that, we assume a time scale of interaction, which is going to be a certain rate that the clouds are arriving to the, for example, the inner parsec, and this time scale increases as the semi-major axis decreases because you are decreasing the cross section. So this is 0. So this is just a parameter that we put, and this time scale decreases with time, and we can write now the same thing, but now as a function of time. And time, I go there, 10 to the 4, what is a function of this rate, which is unknown, at least at the beginning. And this goes like this. So this is 3.0, this is 1.0, 0.5. And of course this is the same f equals 0, f equal 0.5, and f equal 1. Can you imagine why this is more inefficient than the other two? Why for f equals 0 you need a lot of clouds in order to evolve the...
Yeah, more aligned.
You have much more aligned encounters which go in the other direction, expand the binary. But the total evolution is always decreasing. And finally,
am I right saying that most of the events, even in the F0 case, are perpendicular?
no, I think you don't. You have more or less equal probability between these 4 different.
Between the four, right? But the
And you are-
PF and the PA are both perpendicular, right?
You're
And the
right.
PF and the P. So if you put all the perpendicular together, are definitely more than the other.
Yeah, I think you're right.
Yeah.
Yeah, I think you're
That's
right.
good, because
And they are both algebraic in shape.
it's effectively a random walk, but in this case, instead of random walking, it's
It's a
more
byte.
likely to go the other way.
Exactly. And the only difference with random walk is that now you're changing the binary mass, because of course you are repeating, and the process is much more inefficient with time. So we take into account that. So finally, using this result, we made a very simple semi-analytic model in order to compute a time scale for the total evolution in order to get to the gravitational wave regime. So we write the evolution of the semi-major axis as some eta parameter, and of course we know that I erase it, but the evolution of the semi-major axis is a function of the accreted material. So we write it like this. and of course, as for units, we need A. So we have this efficiency, which is going to tell you the average fraction for every encounter. And also the evolution in mass, which is some delta of the cloud mass. Okay, and with this, we can write, we're using this timescale that we put here, we can write a differential equation for the evolution of the semi-major axis. This is going to be eta delta 0 x squared m, and the equation for the mass is cloud 0 a. So now we have a couple differential equation system, and we want to solve this, but of course in here we're not considering the gravitational wave emission, so we put it in our, I'm not going to write the entire expression, but we put the gravitational wave term here, and we solve